In this video, we're going to make some connections between factors of polynomials and their graphs. So first, we are going to use factoring to break down polynomials in general. In the last section, we spent a lot of time talking about ways to factor quadratic polynomials. In this section, we're going to be working with higher degree polynomials. Then we're going to observe some behaviors of polynomials with specific multiplicities. This word may sound familiar to you. If not, we are going to talk about it today, so not a big deal. And then we're going to use information given multiplicities of zeros of polynomials, and we're going to kind of work backwards and derive a possible equation for the function and even make a sketch of what its graph may look like. First, we're going to find horizontal intercepts of this polynomial here. It's a little fuzzy, but we've got x to the sixth minus 3x to the fourth plus 2x squared. Okay. Take a second and try and find all of these. You're going to use factoring. Go ahead and try this first. Pause the video and find those horizontal intercepts. Okay, so for finding these horizontal intercepts, the first thing we're going to do is remember that our y value is 0 for these intercepts. We have no idea how many of these we're going to have, but let's see. So the first thing that I'm going to do is try factoring. So with x to the 6th minus 3x to the 4th plus 2x squared, the first thing I see I can do is factor out an x squared. And so when I take out that x squared, I've got x to the 4th minus 3x squared plus 2. And this is a trinomial. So I'm going to use the same method of factoring that I've used before, and it's actually going to work in the same way. So I'm going to multiply 1 and 2, and I want numbers that multiply to 2 that add up to -3, and I get -2 and -1. So now my x squared is still there. It's really important that I remember that. It's easy at times to kind of get lost or to like forget these like middle steps of the process, but they're really important. Minus 2x squared minus 1x squared plus 2. And remember that this whole thing equals 0. So now I'm going to use my method of factoring here. Boom, boom. I've got my grouping set up. So I've got x squared minus 2. And I'm going to take out a -1, and I get x squared minus 2. These are the same. So now my final factorization comes out to, don't forget the x squared that was out there to begin with. And then these were in their own, these were the same things in their own factors. So they get this, and then the things that are left over from those terms, got these. So then we've got these here. All right, now, why did we do this? Well, we're trying to find the x-intercepts. So right out of the gate, something I noticed is that I can break this down more using difference of squares. Okay, so if you need to look this up again, look up difference of squares. Factoring, if this doesn't look familiar to you. So this breaks up to x plus 1, x minus 1. And then everything else is the same. I still have my x squared minus 2, and I've got my x squared. So now I have the ability to set each of these equal to 0. So I start here with x squared equals 0. Well, obviously here, if I take the square root of both sides, I get x is equal to 0. So there's one of them. So I've got 0, 0 as one of my horizontal intercepts. Now I'm going to set this equation equal to 0. I get x squared minus 2 equals 0. If I add 2 to both sides, I get x squared is equal to 2. When I take the square root of both sides, I have to remember a plus or minus, okay? So I get x is plus or minus the square root of 2. So now what happens is both of those are going to serve as x-intercepts. So I've got square root of 2, 0, and negative square root of 2, 0. And then obviously I've got my x plus 1, x minus 1. So I set x plus 1 equal to 0 and x minus 1 equal to 0. And from this first equation, I get x is negative 1, and then I get x equals 1, okay, by adding and subtracting 1 from both sides. So here are all of my horizontal intercepts. I've got negative square root of 2, 0, square root of 2, 0, 0, 0, negative 1, 0, and 1, 0. Okay. Now, what is going on here? What happens on the graph at particular types of zeros? So what I want you to notice here is here we unsquared that square and we got x equals 0, which is different than anything else. Everything else every other kind of factor that we broke down, we only ended up getting 1 root per factor. So something special has got to be happening here than, say, what's happening here, here, or here. So when we have a polynomial of single multiplicity, what that means is you could think of it like if this is my x minus h to the p power, h is going to be my root. Okay, that's going to be my root. P is called my multiplicity. And the way that we can think about this is the number of times that a root occurs. If it's got a multiplicity of 1, what's going to happen at x equals h? Say this is x equals h right here. So this is h on the x-axis. If p is equal to 1, that means we just have the factor x minus h. Then what's going to happen is this 0, at the 0, what the graph's going to be doing is it's going to kind of be crashing through. Okay, so in class, the way that I kind of describe this to my students is I say, all right, guys, like we're going to talk about the sound this root makes. So effectively, you could think of it like a crashing sound. Like if I'm going to come through, it's only going to happen once. All right, that's actually the sound this makes. In the same way, if I were to come down at it, that's what it would look like if the root was only present once. Now let's suppose I had a multiplicity of 2. So I still have my root at x equals h, or yeah, at x equals h, but now I've got a double root, okay? We call that a double 0. The sound we're gonna make here is boing. It's gonna bounce off the x-axis. In the same vein, it doesn't have to go off it that way. It could go boing off that way. But ultimately what's gonna happen is it's gonna have this glancing kind of bounce off of the x-axis. All right, now, this third one, where we've got multiplicity of 3, for multiplicity of 2, it doesn't have to be 2. It could also be 4, 6, 8. It really could be any even multiplicity. And for triple zeros, what we're going to have in a triple zero is x minus h cubed. Now, here's the thing. Like with the multiplicity 2, this could be 3, 5, 7, 9. It's just not going to be 1, right? So it's not just odd. So the sound here is a point of contention. I think it makes the sound shpeep. I've heard students say swoosh. I've heard bang, bang. I've heard all kinds of different sounds. Ultimately, whatever rings truest to you is the winner. All right, so let's apply this information. So we have this polynomial, which looks familiar to us. When we factored this thing all the way out, what we ended up with was x squared minus 2, and then x plus 1, x minus 1. Now from this x squared minus 2, we knew that we got the roots plus or minus the square root of 2. So why don't we just go ahead and write it like this? X minus the square root of 2 and x plus the square root of 2. Now this is also going to seem a little trivial. Some of this is just going to seem really dumb. And I get it, but there's a reason for it, I promise. I want to write this x as x minus 0. The reason I'm doing this is so that I can get all of my roots to look like this, x minus h to the p power. So now what I'm also going to do is attach, well, this is a 1 power, 1 power, 1 power, 1 power. So now, here I've got a root at x equals 0. Here I've got a root at square root of 2, which is approximately 1.41. Here I've got a root at negative square root of 2, which is approximately negative 1.41. Here I've got a root at negative 1, and here I've got a root at 1. So this one, the x equals 0, this is a double. And the rest of these are all single because of their multiplicities. We know this is a double root because of that. Okay, so all of these other guys single. So believe it or not, we have everything we need to make this rough sketch. So I know I'm going to need the particular x value 0. Here's about 1. Here's 1.41, or roughly square root of 2. Here's negative 1. Here's negative 1.41, blah, 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 or just the negative square root of 2. Now, let's keep in mind that this multiplicity is even. So the arrows are both either going up or they're both going down, remember from 3.1. Since the leading coefficient here is positive, they're both going to be going up. So there's my end behavior. And now, this 0 is going to be a double root, and the rest of these are going to be single. So now, start up top here, we're going to crash through, push, and then we have to come back up and crash here, push. Now when we get to 0, that's a double root, so we're going to need to bounce, boring. And then we're going to smash through 1, push, and then we're going to smash through 1.41, push, and then there you go. Now, this is a rough sketch. There is no reason that the graph should look exactly like this. We haven't even scaled our y-axis. The important parts are still going to be present, though. The end behavior is still going to be exactly what it is because of what we know about leading coefficient and degree. We also know what's going on with the roots. Now, I understand the end behavior may not seem like a big deal, but let's suppose the end behavior was opposite. Well, then when I think about this sketch, it would be a mirror image, which is a big deal. It's obviously a very different picture. So what we really want to do here is make sure that we remember to consider that end behavior, because if we don't, we could have quite literally the opposite graph that we need. Now, ultimately, the goal when we factor every polynomial is to get it looking like this, where we've got this a value out front, and we have these nice lists of factors with multiplicities attached. So this right here is this is an okay factorization. This is really what we're going for, where everything just has a linear x and a root directly attached. This one doesn't, this form is not great because of this factor here, x squared minus 2. Here we see that there's no polynomials greater than linear listed. Okay, so let's write an equation for a polynomial given these features. Go ahead and pause the video and try this on your own. Okay, so we want to write a polynomial. So if you notice, we're saying a polynomial, right? We are forced into a particular polynomial in this case because of this information, but we'll get to that. So we know that we're going to have a polynomial. So we're going to have the most ideal way to write it, which is going to be a, and then a bunch of factors with respective multiplicities attached. So we've got roots of multiplicity 2 at x equals 3 and x equals 1. So if I've got some at x equals 3, the factor is going to be x minus 3. And this is going to be a root of multiplicity 2, so that's going to be squared. I also have one at x equals 1, so its factor is going to be x minus 1. And that's also going to be squared because it's a multiplicity 2. Notice how I kind of changed the sign here, how I reverse them. Okay. If we have, and we notice that on this page here, if I've got x minus h, I've got a root at x equals h. So I'm going backwards. I'm telling you that at x equals 3, I've got a root, so I have to have a factor of x minus 3. Here I've got x equals 1, so I have to have a factor of x minus 1. Okay. And now I've got a root of multiplicity 1, so we know this factor is going to have a multiplicity of 1 at x equals negative 3. So same thing here. If x equals h, this is going to be x minus negative 3, which we know is just going to be x plus 3. And it doesn't tell me anything else about any other roots, so I'm just going to go ahead and get rid of this. And I'm not going to write the 1 there because that's silly. Now, again, a value. It's probably become a sort of trend at this point where it's like, oh, good, here comes the a value. So now we're going to use this coordinate pair to solve. We've got y equals 9 when x equals 0. So now I've got 9 is equal to a 0 minus 3 squared, 0 minus 1 squared, 0 plus 3. So I get 9 is equal to a negative 3 squared, negative 1 squared times 3. So 9 is a times 9 times 1 times 3. So I get 9 is equal to 27a. Divide both sides by 27. So a is going to be equal to 9 over 27, which reduces to 1 over 3. And so now I know my a value. So now my final resulting polynomial is going to be 1/3 x minus 3 squared, x minus 1 squared, x plus 3. Now, this is going to be the polynomial case. It's not just a polynomial, it's the polynomial, because when I send this polynomial through the coordinate pair 0, 9, it forces my a value to be something in particular. If I don't have another coordinate pair, suppose I just didn't have this like vertical intercept information present at all, I could make the a value anything I want because I only know information about the roots. Okay. So just keep that in mind. Go ahead and pause the video and try this one. So we know that the polynomial is of degree 5. So since we have a polynomial of degree 5, another way you could think about this is I'm going to have 5 factors. I'm going to have 5 factors. Now I may have some that are repeated, which is okay. So I've got a double 0 at x equals 1, which means I've got a factor at x minus 1. Since it's a double 0, I can put x minus 1 in here twice. And a triple 0 at x equals 3. So that means I've got the factor x minus 3. Since it's a triple 0, oh man, I just realized I can't count. So I should have had 5 factors listed there. That was dumb. And this isn't like my favorite way to write it. So I'm just going to write it with the squares without making any glaring mistakes here. make my 3 look like a 3. So now I know that it's passing through the point 2, 15. So what I'm going to need to do is make my y value 15, and my x value is going to be 2. So let's do that. So my y value is 15, and my x value is 2. So 15, 2 minus 1, that's 1 squared. 2 minus 3, that's negative 1 cubed. Negative 1 cubed comes out to be negative 1. So I get 15 is negative a, divide both sides by negative 1, or really I could just negate. So then I get a is equal to 15. Okay. Or negative 15, I'm sorry. So my final polynomial comes out to be negative 15, x minus 1 squared, x minus 2 cubed. Okay. All right, the last example, I'm going to give you a graph, and now what you're going to do is determine a formula for the polynomial function graph. Again, this is a the polynomial issue, but it's okay. Go ahead and pause the video and work on this problem yourself. All right, so first, I've got a 0 at x equals negative 3. That means I'm going to have a factor at x plus 3. So we start with our polynomial, and I know I'm going to have x plus 3. Also, observe that I'm going boing when I hit the x-axis here. So that's going to be squared. I could write 4th or 6th or 8th or 10th. This is where the a polynomial is actually okay. All right, now let's observe what's happening here. I've got a single root at x equals 1. So I've got a factor of x minus 1. And since it's crashing through, that's going to be the first power. And same thing here. I've got a root at 3. So I've got a factor of x minus 3. And since it's crashing through, it's going to have a power of 1. All right, now observe as well. I've got this coordinate pair here, 0, negative 2. That's everything I need to find my a value. So now we do that. We say, okay, my y value is negative 2, and my x value is 0. Notice I'm not writing the first powers at this point because we already know what's going on there. So then I get a 3 squared, negative 1, negative 3. So I get negative 2 equals a times 9 times, well, negative 1 times 3, that's just going to be a 3. So I get negative 2 equals 27a. Divide both sides by 27. I get a is negative 2 over 27. And that is my polynomial. Now, let's think about this a value being negative. Does this a value being negative seem okay? I would say so, because if the a value is negative, and look at the degree, 2 times plus 1 plus 1, 2 plus 1 plus 1 is 4, so the degree is 4, and the a value is negative. So since it's even, both arrows are either going up or down. Since this leading coefficient is negative, it makes sense that both arrows are going down. So using information from 3.1, you see that we're going to kind of be circling that almost every place we move in this chapter. So it's really important that you have your vocabulary down for that. And that's 3.3.